Good evening. How's folks doing today? Good. I'm very curious. How's are folks ready for the exams? No. Okay. Well, we're glad that you're here, especially the exams coming up. So we really appreciate the young audiences who are very loyal to our show. And again, as usual, we thank the varsity for hosting us. And please, if you're hungry, take some food from the champs, or if you are thirsty, and you should be thirsty, please go up to the bar and please tip a bartender very generously. Okay. So this is the last show of the year. Today we have two speakers. Both of those are working at LSU. One is a postdoc and the other one is graduate student. So let me introduce you to the first speaker, um, Carlos Gary-Bicas. Um, he was born and raised in Mexico City and have always had a passion for space and science. He went to the University of Colorado at Boulder for a degree in astronomy and to Stony Brook University for a doctorate in planetary science. Currently, he is a postdoc researcher at the Department of Geology and Geophysics at LSU, and his research is focused in understanding surface and subsurface compositions in terrestrial planets with application to astrobiology. And without further ado, let's welcome Carlos to the stage.
How about a big hand for all the AOT people? They're volunteering for all of this, So yeah, my talk is called My Geochemical Ast Romance. It's a play on the popular band Chemical Romance. I am not emo, even though I color my hair, get sad sometimes, and listen to sad music. I'm not emo, I promise. So where does this talk stem from? I love to study Mars. Mars is such a great place to study for a geologist or a planetary scientist. And why is this the case? Well, it is the geologist's playground for two reasons. It doesn't have plate tectonics like Earth, so its crust doesn't recycle. And it has a very thin atmosphere compared to Earth, so there's no weathering going on. So the materials that you have on the surface of Mars are extremely well preserved in contrast to the majority of the materials that you will see here on Earth. So it is the geologist's playground. Now, in terms of how do you study the materials themselves, there's many ways to do so, but the most simple way or the most elementary way is through the periodic table. So this is not your grandmother's periodic table, this is your astronomer's periodic table. All of these elements show where their origin is from. They mainly form from, explosions of stars or mergers, et cetera, et cetera. Now, the elements that are most interesting for Mars itself are the ones that I'm highlighting here. So the red ones are what we call rock-forming elements, or elements that make up all the rocks on the surface of Mars, and even here on Earth. Now, you also have the green ones, which are very important to understand processes on Mars. You will notice that the majority of these elements form through white dwarfs, supernovae, or through dying high-mass stars, with the exception of thorium and uranium, which form through merging neutron stars. So what can elements tell us? Like, what can we understand or learn from elements on Mars? Well, first we need to figure out how to look at them. And this is how we do it. We use this instrument that is currently orbiting Mars up until today. It's a satellite that has many instruments, but there's a suite of instruments on the satellite itself, highlighted in red, that do something known as gamma ray spectroscopy. And I'll get into detail on that in just a second, but I want to highlight something about the Mars Odyssey mission. So this mission was sent out to Mars in 2000. It got there in 2001, and it has completed 60,000 orbits. And so to give you some historical context as to how long this thing has been on there, I want to do a reference to pop culture. So the most popular movies at the time were these three. Just for reference, two of these are getting remakes or offshoots or something like that. And one of these is being used for meme culture for the last 10 years or so. Now, if you want to add insult to injury, this is the most popular cell phone at the time. It's the Nokia 3310. This cell phone was indestructible, and this is why it is the greatest cell phone of all time. It surpasses iPhones and Androids. You could throw this from a 10-story building, and it still would survive. Try that with your iPhone. Anyway, going back to the gamma ray things. Okay, so there are many ways that we can detect elements on the surface of Mars, but the best way to do it so far is looking at neutrons and gamma rays. So on the left, you'll see a diagram as to how gamma rays are emitted and neutrons are emitted from the surface of Mars. So what happens is there will be incident cosmic rays hitting elements, and many things will happen. Some neutrons will get excited and be shot off, like thermal and epithermal neutrons or fast neutrons. Some of these will collide with other elements on the surface, and this will lead to an emission of gamma rays. Some of them will even be captured and gamma rays will be emitted. So each element will have its own gamma ray signature, and this is what you're looking at on the figure on the right. This is a spectral curve depicting gamma ray emissions from different elements, and you will see in the horizontal axis, or some people call it the x-axis, that specific elements will have specific emissions associated to them based on energy. Now, how are you able to retrieve this? Well, you orbit something around Mars and constantly try to passively perceive these, and you will have these emissions. So this mission actually was able to do that, and they were capable of actually detecting 9 different elements. And these are the elements that the mission was able to detect. On the right, you're seeing 2 global maps and their errors based on abundances for, in this case, thorium and potassium. And so this is really, really great, because now you are capable of doing a lot of geology and geochemistry with just these abundances. And just to recall, these are the rock-forming elements, and these are very important because they tell you a lot about the history of the planet. So moving forward, me as a scientist, I have to do a little bit of science. This is your typical scientist experiment where you have an input, you have a black box, some magical machine or code or something will convert the input into an output. But what I did is, I'm going to describe it a little bit better. I took those 9 geochemical maps, I applied machine learning, which is this magical black box, and then I was able to delineate separate geochemical provinces. I was able to basically crush 9 maps into regional contextualized locations. And this is what this looks like. So this is a map of Mars, and each sort of like color-coded region is a specific province that has abundances associated to them. I was able to detect 7 different provinces, and I am going to talk a little bit about one of them because it is very, very significant. So keep your attention towards province 6, that little horn thing looking thing at the bottom right. So we're going to look at other elemental abundances that are useful to try to understand how weathered or aged a region or material is. With those and the rock-forming minerals, you can use more black boxes, or in this case, chemical indices of alteration, to try to understand the history of Mars. This is a ternary diagram. So for non-geology people, this diagram is telling you there are 3 variables being plotted in this triangle, and the regions are associated to these 3 values. Now, the values specifically are called weather indices, so these are different indices used in geology to be able to see how weathered or transformed a region is based on their elements and compositions. And I want you to take a look at that blue circle or blue dot in the bottom left corner. What this diagram coupled with that blue dot is telling us is that this region is the least weathered in contrast to all other regions except province 3, or the yellow dot, but we don't care about the yellow dot. I don't care because it doesn't work for me. So going back to the province itself, if you look at the map, there is a white outline. And this white outline is what previous studies had designated as basically a continent on Mars. And I promise I didn't fudge the numbers. It just so happens that the province that I identified, province number 6, matches in shape to this continental crustal block. So based on my analysis on geochemistry and previous analyses, we basically have a region that is not changed at all. It's very ancient. If you do crater counting, this is how you age surfaces on other planets. This specific region is between 3.7 or 4.0 billion years old. So it's unchanged. There's no chemical changes. There's nothing that's really changed on the surface. So what this is telling us is this is the most well-preserved region on Mars and possibly the entire solar system. This is great news for a lot of geologists. I know it's not as exciting for the layman person, but this is incredible news because now if we look at this region and study it in detail, we can try to understand the processes that form the other planets, including our own. All right, now I'm gonna hop on to other elements. I didn't cover these two. These are actually pretty popular because they are known as heat-producing elements or radioactive elements. And these are very, very important because they can tell us a lot of history about the, temperature and radioactive environment within Mars's crust. So what can we do with these? I know it's finals week, and now there's more diagrams and equations coming. I'm so sorry, but that's just how it is. So there was a study in 2023 that found that these specific elements have a very, very interesting abundance at depth in the crust. It usually was thought that the abundance was constant as you went down into the crust. But this study found that they actually increase exponentially with depth. So if you go to the very bottom of the crust, they are exponentially more abundant than they are at the top of the crust. So this kind of got me thinking, if their abundances are exponentially increasing, what about the radioactivity? Here are the equations I told you I was going to show. So there's actually a very easy way to calculate radioactivity with elemental abundances for these elements. That equation that you see in the top, which is just an addition, is just multiplying the elemental abundances by some empirical values that some person, some dudette, somebody went around on Earth and tried to find out empirically what the relationships between these were. But this is at the surface. We need to figure out what it looks like within the crust. So thankfully, I did pay a lot of attention on my calculus classes, and I derived the equation that you see in the bottom there, which is an integral. It just is telling you that the sum of all of these values at depth changes based on depth, and you can see that it's a function of depth, so you can actually estimate at specific depths what the radiation is. And that's exactly what I did. And this is what this looks like. So on the top right, you will see a map that shows, the radioactivity at about 10 meters depth. Now you're gonna ask me, Carlos, why 10 meters? Well, so Mars doesn't have an atmosphere, as I mentioned. It doesn't even have a magnetic field. So what happens on the surface of Mars is, if you're on the surface, all the radiation that comes from the sun and the galaxy and everywhere is basically gonna cook you. So it's unsafe. It's not safe to settle those regions. You have to go deep, actually 10 meters deep, to be able to be shielded from all that radiation from space. And so I calculated what the radiation from the crust, not from space, looks like, and this is what this map looks like. Red means really radioactive, and blue means not that radioactive. But interestingly enough, if you compare the values of radioactivity from Earth to Mars, you will see that Mars within its crust is even less radioactive than here on the surface. So we're being poisoned here right now more than we would be 10 meters deep into Mars, which is not great, but I mean, it is what it is. And that's literally what these histograms are showing you. On Earth, the average adsorb rate is about 60 nanograde per hour. On Mars, the average is 6 to 7, so 10 times less. So you don't want to die of radiation, go to the crust on Mars, I guess. But you're going to ask me, well, Carlos, they introduced you as an astrobiologist. I'm not, but I do astrobiology. It's very different. How does radiation apply to astrobiology? And to that, I needed to look at studies that have been very, very merciless with microbes on labs. And this study was actually pretty good at trying to identify how bacteria could resist to constant radiation. They look at this bacteria specifically. It's called Deinococcus radiodurans. And they put it in different scenarios or situations in terms of like the environment. So you had aqueous, desiccated, frozen, and desiccated and frozen. Mars more than likely resembles the desiccated and frozen case. And so interestingly enough, this study found that bacteria will survive up to 140 kilograms of radiation if it is in desiccated and frozen environments. And well, not bacteria, this bacteria. So it's like, okay, I have the resistance of bacteria to getting destroyed by radiation. I know what the radiation rate at 10-meter depths on Mars is. Let's calculate how long it would take to kill the bacteria at the crust if it was there. It's very easy. It's just a division. And this is what this map is showing. So top right map shows you a map of, it's up to your interpretation, survival or destruction times for Deinococcus radiodurans at 10 meters if it were to live on Mars. I want you to pay attention to the temporal range. We're talking about between 800 million to about 2 billion years to kill bacteria on Mars. This is huge because I just told you earlier that most of the surface on Mars is unchanged. So if most of the surface on Mars is unchanged for billions of years, and we know that the radioactivity would take so many years to kill bacteria, what this is all telling us is there's a high likelihood that bacteria, if it were like Deinococcus radiodurans, would survive between 800 to 2 billion years, 800 million to 2 billion years in the subsurface of Mars. On average is 1.24 billion years, but I mean, there's places in red that tell you these are the locations where it will survive. I know I put it in high caps. Please get me published. I'm working on this. If you know your editor, please let them know. In any case, I'm gonna wrap up. Some closing remarks. I'm very corny, so elements are like elementary, dude. They're useful to calculate crustal formation and alteration histories on Mars. You can also actually calculate how long microbes could possibly survive in the crust on Mars. The Nokia 3310 phones were better than anything today, and yes, I will die on this hill. Again, I am not emo, and please, please, please make sure to tip your bartender well. Thank you so much.
Thank you, Carlos. We have time for a few questions.
It's a great question. So I'm going to paraphrase it as best as I can. It looks like Mars is going to be the new frontier of settlement, so Wild Wild West. And bolo ties might be a thing. And most bolo ties have blue stones instead of red. Does Mars has blue stones? I would argue it does. You just have to dig a little deeper. So all the red that you're seeing on Mars is just super oxidized or iron-rich material. But the further down you go, the more, let's say, variable the material properties are. So we could probably find, I'm not gonna say we could find some agates. Like, if a geologist is in the room, he's probably gonna strangle me at this point, but a real question, yeah. Okay, so in a very, very short form, is it possible to terraform Mars? Short answer is no, and it's because Mars, as I mentioned before, it just doesn't have a magnetic field, and that the magnetic field that we have here on Earth is insanely good at protecting us from anything that's radiation based in outside both solar flares as well as the galaxy. So if you can figure out how to make a magnetic shield on Mars, then yes, we probably could survive. But other than that, like I'm not even gonna go into like the theory of atmospherics, but it's even worse without a magnetic field. I refuse to answer this question. So I said the question was, if you claim that the Nokia 3310 is better than all phones that we have right now, what phone do I have on me? Again, I refuse to answer this question. Next question. What's my favorite Pokemon? Torchic. Question. So the question is, what black box machine algorithm did I use? So it's two separate machine learning algorithms. One is a dimensionality reduction algorithm. It's called T-distributed student stochastic neighborhood embedding. This basically takes data sets that are multidimensional, think 9 geochemical maps, and compresses them into a smaller dimension. The second one is a clustering algorithm that clusters the dimensionality reduced data sets. It's called HDV-scan. It stands for something that I cannot remember because it's a long acronym, but all I can say it's much better than the stuff they used before. Trust me. I mean, it's not published yet, but we're working on it. Yes. Okay, yeah. So are you talking about like these dark features? Okay. So these two dark features, especially in the southern hemisphere, are crater impacts. This is Hellas Basin and this is Argara Basin. These are technically the largest crater impacts in all of the solar system. Um, they basically deformed all of the terrains around them. The reason why there's such a significant bias in the results at these specific locations, especially if you look at the error plots, is because these regions are actually not crustally thick. And so the model that I used looks at crustal depth in contrast to the materials. And so this is a very thin region, and my model's telling me, like, don't trust any of these locations, which is really good news for me because this is usually what the science agrees on. Another question from the stranger who is my friend. I guess he's not my friend. I'm gonna get in trouble. There's no way to answer this question correctly. So basically, I'm getting asked a way to tie in the elemental compositions of Mars to masculine energy. No, there's no good way to answer this right now. All I'm gonna say is maybe it will. I will say this. I don't know if y'all heard this, but they just found on a asteroid a significant amount of tryptophan. So you know, there might be some relation there. I don't know. It's not a Mars satellite. I can talk to you about that later, friend or not friend. But to answer the masculine question, it's interesting because technically speaking, Mars is the second smallest terrestrial planet in our solar system. It is the reddest. It is on the surface.
Sorry, I have to count the time's up. Okay. Let's thank Carlos again, and let's wish him a good luck with his publication. Carlos has been a very enthusiastic speaker for AOT. As I believe Carlos has spoken at AOT twice this year. We love Carlos. All right, so now we are going to have a short intermission for about 10 minutes. As usual, we have trivia on the screen.
Heaven knows that I'm born too late for these ghosts that I chase. With these dreams I inflate, painted skies in my brain. Every day I'm forsaken in space to escape this old world, this old world. Some days I lie wide awake till the sun hits my face and I fade, elevate from the earth far away to a place where I'm free from the weight. This old world, this old world. Don't trust anything or anyone below the sun. I don't feel anything at all. I'm king of the clouds, of the clouds. I get lifted, I get lifted. King of the clouds, of the clouds. I get lifted, I get lifted. Inside of my mind, I'm ascending these ladders. I'm climbing, say goodbye this whole world, this whole world. And when I fall to rise with stardust in my eyes, in the backbone of night, I'm combustible dust in the fire. When I can't sleep awake, I'm too tired. This whole world, this whole world. I don't trust anything or anyone below the sun. I don't feel anything at all. I'm king of the clouds, of the clouds. I get lifted, I get lifted. King of the clouds, of the clouds. I get lifted, I get lifted. Imagination take me somewhere I don't know. I'm lost but I'd rather find it.
Sound it seemed to fade, came back like a slow voice on a wave of fate. That wasn't no DJ, that was hazy cosmic jive. There's a starman waiting in the sky. He'd like to come and meet us, but he thinks he'd blow our minds. There's a starman waiting in the sky. He's told us not to blow it, 'cause he knows
we are about to welcome our second speaker, Max, who is a graduate student at LSU. He's a second year physics graduate student studying gravitational theory and quantum gravity. Very exciting. Max received his undergraduate degree from Oregon State University, where his research focused on the mathematical foundations of quantum mechanics. His current research interests include quantum cosmology, loop quantum gravity, and the geometric approach to quantum mechanics. In his spare time, he enjoys challenging gravity in other ways, such as rock climbing and slacklining. Okay. He has never taken me to slacklining, so I have no idea what it is. Let's welcome Max to the stage.
Thanks, Fong. All right, thank you. What is time? To begin, I'd like to start by asking a related but slightly different question. What time is it? This is open to the audience. Does anyone have the time right now? 7:41. How do you know? You looked at your watch? You looked at your phone? Okay, great. So you looked at a clock, right? So time is what a clock measures. That was an easy presentation. Thank you. So I kid, but it does get at something sort of fundamental, which is that although we have a very intuitive notion of what time is and how it interacts with our day-to-day life, it's a little bit tricky to actually probe at what it is on its own without reference to some other system. Thankfully, in physics, we have methods that we can use to deal with that. Unfortunately, it does require some math. So hold your booze, not quite yet. So don't worry, I'm not going to make anyone do any calculus during this presentation. But there is something to be said about the way that mathematics and the laws of physics interact, and that they have a very deep interplay with each other. And it's really not possible to have physics without math. And so while we're not going to go into depth in these equations, I want you to remember these 5 equations from thermodynamics, special relativity, general relativity, quantum mechanics, and quantum gravity, sort of as landmarks throughout our presentation and puzzle pieces that will maybe help us put together this question of what is time as we go on. So going pretty far back in time into antiquity, people have been thinking about time for about as long as people have been able to write about it, at least, and probably able to think about it. People have wondered, in its totality, does time cycle around? Is it endless? Does it have a beginning and end? And in particular, at least from what we know from past writings, a couple of ideas that were prominent, at least in Europe and Western philosophy, came from Plato and Aristotle. Plato thought that time was related to the motion of heavenly bodies. So, Mars goes around the sun, and we can tell what time is because of what Mars does. And Aristotle takes that a step further by saying time does not exist on its own, but it only exists relative to the motion of objects. And while this isn't mathematically based, this formed a lot of thought about time for some time, until the time came when Isaac Newton came along and threw everything on its head. And Isaac Newton really put formality into the laws of physics with his laws of motion, which uses physics on a background coordinate system. And so with this, it's really useful because you can do things like tell how a ball moves on a trajectory as you throw it, or how planets orbit the sun. And what it does is it introduces this background coordinate system, where in particular there's this absolute notion of time, where there's a clock ethereally out there in the universe that goes from past to future, and everywhere runs on that clock. And also, it's worth noting that it's time reversible, so there's no reason to say why time goes from future to the past or past to the future. There's nothing in the laws of physics, as Newton proclaimed them, that tells you the direction. This troubled some people for some time until about the mid to late 19th century, when thermodynamics started to come into the picture. And in thermodynamics, we don't talk about single objects like a ball on a trajectory, but we deal with large ensembles of objects and deal with, as people later found out, the statistics of this large ensemble. And one particular concept that's crucial is entropy, which colloquially, it's the disorder of a physical system. And it characterizes the probabilities, the statistics on these ensembles of objects. And one crucial thing we found was the second law of thermodynamics, which tells us that entropy always increases over time. So the rate of change of entropy is always more than zero. You can think about this intuitively if you dropped a little bit of dye into some water. As time goes on, the dye is able to spread out throughout the water. And so, this picture comes after this picture because the entropy is increasing. It's exploring more of the states of the system. So entropy gives us something that tells us that, it's a thing that's not time reversible. And I want you to just keep that in the back of your head as we keep going on. So we have an okay picture that's relatively intuitive to our current notions of time. But once again, another someone comes along, this time Albert Einstein, and throws everything on its head with his theory of special relativity. And in 1905, he proposed these two postulates. The laws of physics are the same in all inertial reference frames, and the speed of light is the same in all inertial reference frames. And the somewhat surprising conclusion from these relatively simple statements is that space and time are not separate, but part of the same entity, space-time. And this might not seem super obvious at first, and I did plan on having a larger stage to do this, but we'll see how this goes. I have a flashlight here, and if I shine it, right now we're all in the same reference frame. We all see this going at the speed of light. But if I was to run across the stage and, not fall to my death afterwards, for that moment where I was moving, nothing has really changed for me because the flashlight's still in my hand, I'm in my own reference frame, and I see the speed of light going forward. But you see me moving, and normally from Newtonian physics, you would expect then with me with the flashlight in my hand, the speed of light would be whatever I saw plus whatever I was moving. But actually, you see me moving, and you see the same speed of light as I do. So something has to give there. And since speed is just a ratio of distance to time, the thing that has to give is our notions of space and time. And in particular, there is no universal notion of time as Newton proposed it. Time passes at different rates for different observers. If you've ever heard of time dilation, that's what this is. And more than just this time dilation, the absolute notion of time changes in cause and effect from Newton's theory. So on the left here, we have what's called a light cone, where we have an X and Y axis for space and a time axis. And we imagine these edges of the cone as speeds, ratios of distance to time that go out at the speed of light. And while we can have things that are less than the speed of light as an absolute future of our point, and things less than the speed of light as an absolute past, there is this region around the middle that's neither. It is what we would call causally disconnected. And as a very helpful tool that we'll also utilize later, this is called a Penrose diagram, where basically we smush all of space-time into a finite region. You can see there's a region here that's the future, and a region here that's the past, bound by the speed of light, and a region outside that is causally disconnected. Now, relativity tends to freak out, especially, like your modern physics student, because it sends you into a crisis of, well, if everything's relative, how do I do physics? But there are things that we can actually calculate and do not depend on the observer. And one important one is the space-time interval, which is basically this thing where if you square it, it's equal to a change in distance squared minus a change in time squared. And to try to relate this experience to something you might know more, it looks a little bit like the Pythagorean theorem, a squared plus b squared equals c squared. Hopefully most people have at least heard of that before. And that gives you distances in Euclidean space, in Euclidean geometry. But here we have this interesting minus sign. So rather than flat Euclidean space, as we would typically conceive it, instead in special relativity, we have this hyperbolic geometry. If you've ever seen a hyperbola, it's this sort of shape. So it is geometry still, but fundamentally different than the type that we learn in school. Now, Einstein, over the next 10 years, was able to develop these ideas into something much grander called general relativity. And in this, we extend it to curved spacetimes. So if you want to try and think of it, it's like lots of more really complicated Pythagorean theorems everywhere in space. And not only does he talk about curved spacetime, but he also tells us why it's curved. And that brings us to the Einstein field equations, which tells us that the curvature of spacetime, you can kind of see it in this artwork here, is given by the matter and the energy in your spacetime. And consequently, things move in this curved spacetime. And this brings about a famous quote by the physicist John Wheeler: space-time tells matter how to move, and matter tells space-time how to curve. And this gives us gravity. So the curvature that we get in space-time and the movement that it tells matter to do is how we get that attraction from gravity. And something even more sort of crucial to our further discussion is that this is a background independent theory. So there's really no preferred choice of coordinates anywhere in this theory. Time is just one of the other variables coming along through the ride. You can't even agree on it if you're at over here or in here. It's just a parameter. The space-time exists independently of the space or the time. And that brings me to one of my favorite quotes about time from the great physicist Hermann Minkowski. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. And to really get a grasp for that, I want to take us through a few examples to see how this comes about in real scenarios, like out in space, that astrophysicists can look at. So the first one, and maybe counterintuitively the most simple, is black holes. And black holes were formulated only a year after Einstein first published his first papers in general relativity that had the full theory. And it really just comes down to a spherically symmetric static spacetime. So you have a sphere in your spacetime. This gives you the Schwarzschild solution for a black hole. And there's a couple really important things that come out of it: the event horizon, which is like the edge of the black hole, and the singularity, which is the center of it. And here we have another Penrose diagram, which you might notice looks a little different. Once you get to this event horizon, what actually happens is in one of those little Pythagorean theorems, the part that goes into the black hole, this spatial part, and the time part switch sides. So once you get inside the black hole, going to the future actually has that negative sign with it on the radial part. So going further into the black hole is the same as going further in time. And so you might think, well, you've maybe heard at least that once you get inside the black hole, the gravity is so strong that not even light can escape. And the reason that happens is actually from this causal structure here. The future is inside the black hole. It cannot be outside of it. Once you're in here, it's causally disconnected. And the other thing to note is this singularity at the center. And what happens here, it's like a boundary of this space-time curved manifold is what we call it. And it's really not even a point in space-time, but it's a point where our equations break down. It's like dividing by zero. It's a place that's not somewhere, and it's a time that's not some time. So keep that in mind as we keep going also. A second case, which has a little bit of a similar problem, is cosmology and the Big Bang. So you might have heard that the universe is expanding, and that's something we can calculate from Einstein's field equations for just matter distributed throughout space-time. And if we trace that backwards, what we eventually get is a point where the volume of any region goes to zero. And so if we look at that on a Penrose diagram, you can see in this future part, it looks a little bit like that special relativity example. But once we get back, we just have this straight line here. And this is another singularity given by the Big Bang. So no matter where you are in the universe, it doesn't matter when or where you are, but the Big Bang will always be in your past. It is a singularity that all citizens of the universe can see. And finally, this is also just a word of caution about mathematicians, because there's a reason we don't have mathematics on tap. They get a little too crazy. You can have what's called the Gödel universe, which was formulated by mathematician Kurt Gödel. And instead, you get a cylindrically symmetric rotating universe. So like imagine all of the galaxies and everything in the universe spinning about an axis. And in this case, it distorts space-time so violently that any time-like path you go on will end up going in a closed loop. So you have closed time-like curves. So in this universe, you can time travel. So any of you time travel aficionados, all you have to do is get the entire universe spinning and wait for the entire lifetime of the universe. And also you can't change anything because you get back to the same place. So this is a cool example, but it's not physically realistic. And I worry we've gotten a little bit ahead of ourselves. So let's see what people have been up to during this time in the rest of physics. Uh-oh, nothing happened. There we go. Just kidding. One of the great tour de forces of mathematical physics, other than general relativity, that happened in the 1910s was Noether's theorem, which was by the mathematical physicist, I should say, Emmy Noether. And this tells us that there's a fundamental duality between the symmetries of the universe and its conservation laws. In particular, if there's a continuous symmetry, there's a corresponding quantity whose value is conserved. And the case of this that we're really interested in here is energy, because the conservation of energy by Noether's theorem is related to time translation symmetry. And this is something we'll probably see for the rest of the talk, is that there's this deep connection between energy and the way that things move through time. Into the next decade, we started to get the other main cornerstone of modern physics, quantum theory. And in a nutshell, if you just want the one-sentence version, quantum mechanics is our theory of small stuff, molecules, atoms, particles. Of course, there's a whole, mathematical universe waiting for you if you wish to discover it. But what we really need here is that the radical change in physics that we get from quantum mechanics is that it's inherently probabilistic. You can only talk about probabilities moving in time instead of deterministic things changing in time. But on the flip side, we really just keep this old Newtonian notion of time where it's this constant thing in the background. So it's not radical in that sense. So what I have here, you can imagine this as like a probability density of like an atom or something changing in time. But it's really just a background time parameter. And the way we describe this is with Schrodinger's equation, which you might have seen before, which essentially tells us the way that quantum wave functions move in time is given by the Hamiltonian, which is just a total energy acting on them. And interestingly, you might have seen this before and you think it's really esoteric, it's got an imaginary I and this weird H bar here. But short of those, if you reformulate it in a special way, you really just get classical time evolution, the same as you could get from Newtonian mechanics, the same sort of duality between energy and time that you see from Noether's theorems. Now, this brings us to the crux of the issue in the modern day, which is how these notions from general relativity and quantum mechanics interact with each other. Because on the general relativity side, we have deterministic physics, but time is in the background, or there is no time in the background, rather. It's dynamic. Time is in the background on the quantum mechanics side of things, but your physics is probabilistic. But the issue is we would expect both of these theories to sort of form our fundamental notion of reality. So it's tricky to determine how we can combine them into some notion of quantum gravity with a quantum space-time. But people have tried, and in particular, one of the major efforts in what's called canonical quantum gravity happened in the 1960s with what's called the Wheeler-DeWitt equation. And there's a lot of, terrible math that goes into it, but essentially what you do is you take that 3 dimensions of time, or of space, and 1 of time, and split it up. So you can think maybe like the guy at the deli, cutting your ham. That's Wheeler and DeWitt cutting up the space-time into spatial 3-dimensional slices, foliated by time. And that is something you can't actually try and put into the quantum mechanical equations. And what you get is a totally constrained system. So you'll notice over here, this is our Hamiltonian on the wave function. But over here, this is where we had time evolution earlier. And it's just 0. So we have what's called the frozen formalism. There is no time. Nothing happens. How do we do physics? And maybe you sit around and weep for a bit because reality isn't real anymore. But you pick yourself back up, you try to look at some simple systems, like in quantum cosmology, where everything is very symmetric, and you can actually deal with this. In particular, there's what's called the relational time formalism, where it's clocks all the way down. So going back to what you told me earlier in the talk, time is what we measure on a what we measure on a clock. Pardon me. So instead of things moving with respect to time, we just have things moving with respect to other things. And in particular, we can do calculations in quantum cosmology with respect to internal clocks, so things given by matter in the theory. One useful example is the scalar field. So what I've tried to show here is like you have a field that is defined classically on space-time that you serve as a parameterization, and you can tell how things move in the universe based just on what this field is doing without reference to time. And so finally, looking to the frontiers of physics, ultimately we would hope for a quantum space-time where there's just our notions of general relativity put into quantum mechanics, where there's no preferred time variable. And one idea that I think is a bit interesting is called the thermal time hypothesis, where the emergence of time is singled out by thermodynamics. So there's no macroscopic notion of time that becomes microscopic. It's a macroscopic notion of time that emerges from these microscopic degrees of freedom. So it's a little bit like the second law of thermodynamics, as we talked about earlier, where it's these ensembles from probability distributions that give us our notion of time. But, you know, it's worth noting everything in this quantum gravity section is not stuff we've tested in experiments yet. So whether these will stand the notion of time, only time will tell. So just as some final thoughts, I've brought you through this journey through all these notions of time, and I am aware of the fact that I never really gave you a clear answer of what time was, but I gave you a bunch of the pieces of the puzzle that we can find in different branches of physics. And the analogy I would like to think about it with is with the parable of the elephant in the dark, if you've ever heard about it. There's a group of men in the dark with an elephant, and they're trying to figure out what it is. One grabs the tusk and says, oh, it must be like a spear or something. And another grabs the tail and says, I think it's like a rope. And it goes on like this. And none of them are completely wrong, but they all just have aspects of the truth. And they have to put the truth together from all of these clues. And I think from our different notions of physics, our idea of time is a bit like that. The puzzle pieces are all put in front of us, and it's up for us to put them together now. So with all of that being said, I guess there's nothing else to say, but thank you for your time.
Thank you, Max. Please stay for the questions. Also, please.
Sounds good. Okay. How many times did I say time? I have no idea. I was ad-libbing this whole presentation. So many times. Okay, so MOND is this theory where we modify the Newtonian dynamics of gravity, and it's supposed to instead give an incorporation of dark matter, which is this matter we think is out there from like galaxy rotations. I don't think MOND really fits into this picture well because it's really hard to incorporate with general relativity, which is our sort of a very well-tested picture and kind of gives us our paradigm of time. So I don't really know how MOND fits into that. Yes? Okay, so since there's a singularity at the Big Bang and a singularity in black holes, could it be argued that our whole universe is in a black hole? I know I have actually like seen arguments about this before, and that there's some indistinguishability between like our cosmological space-time and a black hole space-time. Although as a naive answer, I would say no, because Oh, it can't go very fast. Never mind. Basically, the black hole singularity was in the causal future in that like green region, and the Big Bang singularity was in the past in the blue region. So they're kind of different in that notion. Oh, it's going all the way. What's even happening now? There it is. How about that? Yes. Maybe a little basic. My favorite Pokemon. Probably Charizard. Yes.
So since you're the expert, so I'm going to ask a question. Next week I have an exam, okay? So let's say I answer a question with an answer A, but my teacher says that in his reference frame, the correct answer is B. How am I going to argue with my teacher? But for me, in my reference, the answer is A. But for my teacher, in his reference, the answer is B.
So I don't know if A and B are things that depend on reference frame is the issue. I think it might be a little like the space-time interval where it's invariant, but maybe it's something like a time variable. In that case, I think you should plunge either yourself or your teacher into the center of the Earth, and because of the gravitational time dilation, you can get it just right so that in that reference frame the answer is correct.
Okay, cool. Thank you, Max. And now it's time for announcing the trivia answer. Can we go to the question, please? Yes. 1, pancake or moon? Pancake. 2, also pancake or moon? Moon. Number 3, again, pancake or moon? Moon. Number 4, pancake or moon? Moon. Number 5, pancake or moon again? We have pancake. Number 6, pancake or moon? We have pancake. Number 7, pancake or moon? Pancake. Number 8, pancake or moon? Pancake. Number 9, pancake or moon? Moon. And number 10, pancake or moon? Moon. This trivia really makes me want to go to IHOP right now. I have never been at IHOP, to be honest, but I love Waffle House. Okay, so I'm announcing the trivia winner. Oh, this is a hard name. Okay, I don't know how to spell this, so I don't know how to say this, but so I'm going to spell the letter. JUDC. Oh, it's you. Okay. All right. Let's give them a round of applause. All right. And the next thing we have is a raffle. Okay. So please take out your ticket and let's see who is the winner today. Okay. So we have 0, 5, 8. I already hear some yes. 7, 9. Guess what's the next number? 5. Do we have a winner? It's you? All right, let's congratulations. And please go to our table and pick up a free merchant. And that's it. That's the last show of 2025. We appreciate you coming. If you have exams coming up, I wish you will be successful with your exam. Otherwise, happy holiday.